Okay. And let's talk about the sampling and quantization. Okay, the sampling in a signal. Let's say, forget about the image just for a few moments, and then there is a signal like this. Looks like a sine image, not image, sine signal, and then it is recorded. When you think this signal is recorded according to the time, then it is recorded very in a short period. See, let's think that this is 1 second, and then there are several milliseconds. For each several milliseconds, the signal was calculated. Signal was observed, and these signals could be. We say that this is very this curves or this signal is very clear and easy to understand, but maybe all the signals are not important. In some cases, we just need 1, 2, 3, 4, 4 like 8 samples in 1 second. Maybe this is just enough to process or understand this signal. We may not need to take all the signals. Just think that we are checking the temperature of the outside, and how often do you want to check the temperature? Maybe once in 1 hour, or once in a day, or once in a minute. Okay, then we can check the change of the temperature very precisely, but maybe it is not important maybe it is not necessary to check the temperature for each 1 millisecond because they are too similar, right? So according to the purpose, that how often you are taking the signal, checking the states of environments is defined. So it's up to the purpose. Just let's assume that in these circumstances, we need to take only 8 signals. Then we just take the signals. Okay. Then, okay. Okay, this point, and then this point, and then this point. Okay, these points are selected. Then we have 8 data. Then what is good point for just selecting 8? The space of a hard disk, so size of the data could be reduced. And then processing time could be reduced. And computing power, which are necessary to check or process the data, could be reduced. So there are lots of good points. This process, what I just explained, is called sampling. And quantization is approximating values to a number of categories. So here, the original signals are checked very precisely, right? At this point, at every point, the exact values are recorded. So we can see this. We see this is very continuous, but maybe this is not necessary to know exact value of the data. Maybe we just know this is high or low or medium. So maybe we just want to know into the 4 levels. Okay, so if our data is close to this point, or this point, or this point, we want to know that. Then okay, how to clear it? Okay, so then here we sampled this point, and actual value is here, but we want to quantize it. This value is closer, similar to this point, this level. Then we change the value into value as value to here, this point, 1, 0. Just let's say this is 0. This is 0, 1, 2, 3. Then this becomes 2, and at this point the value is similar to 3. And at this point 3 and 2, 1, 0, 0, 1. Then the necessary size of the data are reduced a lot, isn't it? Before to express all the signals correctly, we needed lots of data spaces, and the data size is very big. But now we just know what we need to explain this signal is just 8 numbers, and even the numbers are integer, and to express each number we need only 2 bits. So these are all 8 points, so what we need is just 16 bits, which means 2 bytes. So this is why we are doing quantization. Okay, then what is the sampling and quantization of the image? Okay, this is the sampling and the quantization. The sampling in the image is they're just resizing the image, because the sampling here is selecting a number of the points according to time or spatial axis, right? So as you see, the information becomes pretty small. The information inside here, inside the image, is reduced as the size of the image becomes small. Okay, when it becomes 36 by 21, then it is difficult to understand or recognize what the inside of what the object inside of image is. Okay, and the quantization in the image is reducing the number of colors. Okay, this is the almost original image with using 25 6 levels, and then this is black and white, not black and white, this is grayscale image. So you see, even just using the 256 levels, you see this is very clear, and you will not see the stranges inside the image. But when the levels decreases, then the quality of this image has been reduced. Then finally becomes black and white images. Okay, this is white and this is black. And with using the 2 levels, then still you can see what the object is inside of this image, but the quality decreases a lot. Okay, and let me explain the histogram of the image and the morphology, and let's close today's class. The histogram is the number of pixels, checking the number of pixels according to the color spaces. So I told you that each color axis we have 8 bits of information, which means 0 to 255 in a computer. Then when we are checking and analyzing an image, color image, we can check the color information for each axis. For example, how much yellow pixels inside of these images, how much blue colors inside of these images. Okay, more specifically, in blue axis, how many pixels are there of the value of blue. The value of blue is 5, or value of the blue is 255. Okay, and this is the example of the color histogram. And then, for example, let's see that if this is the color histogram of red, okay, red, then which means there are lots of red, lots of pixels in where maybe this is about 50 or 60, I can't sure. Let's just say this is the color value at this point is 60. Then, which means the color value of 60 for R is pretty much inside of this image. Okay. We can calculate lots of. We can calculate easily. Actually, it's not much difficult to calculate the histogram in these days. Just when you have Python in your computer, then you just call. You may just calculate type 2 or 3 lines. Then you will easily get the histogram of the images. Then where we can use for this histogram. Okay, there are several applications, and here I want to explain about the histogram equalization. Now here, histogram histogram equalization is to enhance an image brightness. Just check these two images. The upper image is the original image. Then when you calculate the histogram, then histogram is just like this. As you see, this is too bright. So when photographer took this image, maybe he made some mistakes. So there are too much light and too bright. And when you check the histogram, then you see the pixels of high intensity is very much a lot. There are lots of high intensity pixels. So here, maybe if we just change, right, these colors into more bright and more dark, and this more dark, and this more dark, and more dark, and then if we make this histogram more equalized, then the signal, the image is the quality of the image may be increased, isn't it? So that's the idea of histogram equalization. This is usually this is different to the changing the brightness. If we just changing the brightness, all the histograms will be moved into the darkness altogether. Then the contrast of the image will not be changed. But when you are doing the histogram equalization, it's not moving all together. Some part is moving slowly, moving a lot, and some part here maybe do not move, or here some part moves a little and this moves a bit more. So this is the converting graph between the previous color and new colors. So if the color value is here, then new color is just to here. Okay, almost same, isn't it? But here, if the previous color is here, then the new color is here. So the difference between these two colors are pretty big before, but in the new color space, can I say this is color space? But in the changed color, between the color difference between these two new colors are pretty small. So in this way, we can enhance the image contrast. Okay, then let's talk about the morphology. Morphology is a technique, image processing technique for the binary images. You see there are two images here, the same images. This image is we say this is a binary image because the information inside of the image is 0 or 1. As you studied before, just before, this image was quantized by the original image. Okay, so using the dilation, using the morphology techniques, we can process and make these images better or worse using the morphology. Okay, let me explain the dilation and erosion. These two techniques are the basics of morphology. Dilation is making an object inside of the binary image bigger. I call this as an object because in the binary image, you see only you cannot figure the color. You cannot figure the object colors whether the object is here and object exists or not. That's only you can figure it out in the binary image. Okay, here the dilation is the concept. The algorithm of the dilation is very simple. If a pixel here, okay, if a pixel here, the value near the pixel, if there is only one, if there is a pixel of 1 near of this pixel, then the new value of this pixel is going to be 1. You got it? So, okay, checking. Okay, let's check this pixel. This pixel is going to be, the value of this pixel is going to be changed. And if around these pixels, if there are more than 1 pixel of value 1, is there any one pixel of 1 is sorry, if there is any pixels of 1 exists, then it becomes 1. Let's talk about this pixel. Around this pixel, there is no 1. All the around the pixels of this pixel is are zeros, right? They're all zeros, no pixels of 1. So then this pixel is going to be 0. And let's talk about this pixel. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right here. Okay, this pixel will not be changed because itself is 1. And then there are 4 ones. Then this pixel, the value of new pixel is going to be 1. Okay. How about this pixel? 1, 2, 3, 4, 1, 2, right here. This pixel is going to be changed into 1 because there are white pixel here. Let's say this is just white pixel. That's a lot easier to explain. And this is black pixel. There's a white pixel here. So then this is going to be white. This is a dilation. And erosion is the opposite of dilation. Let's talk about this pixel. Okay, 4 and 3. 4 and 3 here. This pixel has been changed from white to black because around this pixel there are 4 blacks, right? 4 blacks. So this becomes black. 0. Okay, how about this point? Okay, and this becomes 0. Okay, this point. This becomes 0 because around these pixels there are zeros. Okay, there are black pixels around this pixel. Then it's going to be black. If there is any black pixels around the pixel, then it's going to be black. And then if there are no black pixels, just like this, or white, right? Then it's going to be white. This is erosion. So dilation is an object making an object bigger. So this object, okay, let's make it clear. Okay, this object becomes bigger, and this object becomes bigger too. It has the shape itself. Shape of an object has been not much been changed. Pretty similar, but it becomes bigger. The erosion is making an object smaller. Okay. Just assume that if we took the erosion once again from this image, what happens? Okay, this object will be disappeared because this pixel, around this pixel there are zeros. Okay, around there black exists, and all the black exist around the pixels. There are no pixels without the black neighbors. So which means if we took one more erosion here, then the image becomes all black. All black. No white object. Okay. What happens if we took the one more dilation here? One more dilation, then the white area is going to be more bigger. true. When we do the dilation, then what you see here is these two objects were separated at first, but after dilation, these two objects are connected. Right? This is the main rule of dilation. So if there are two objects near, then they will be connected. If there is a hole inside of an object, it will be filled. What about the erosion? If there are small objects, it will be disappeared. If there are connections of a narrow with a narrow bridge, then it will be disconnected. That is a rule of erosion. Okay, then dilation and erosion themselves are not much used in image processing, but they are often used by combination of both erosion and dilation. If we do erosion and dilation and okay, just I made a mistake here. Erosion and dilation. Then we say this is an opening. We first do the erosion. Okay, erosion here. Then we calculate the dilation here. We calculate the dilation. So image becomes like this. Okay. So if we do the dilation, okay, here, okay, image becomes like this. These looks very similar to the previous image, but it's a little different. For example, if we do the opening, so shapes are, if we do the erosion and dilation, it becomes a little different because if there are very small lines, it will be disappeared. So if there are small holes, and then it could be enlarged. Holes could be enlarged. Closing is applying dilation first and then erosion later. Let's assume that there are images like this. Okay, what happens if we doing the erosion first and then dilation later? If we do erosion first, then this object will be disappeared, right? Then if we do the dilation, then this object will be appeared again? No, because there are no object at all, then dilation will not be applied for this object, cannot be applied because there are no object. So if we do the erosion first and then dilation later, then object will be pretty simple. And then small noises, small objects, well, maybe it could be noises, then will be disappeared. The closing is the opposite operation. The dilation first and then erosion later. When you do that, okay. If we do the dilation first, then this dilation and erosion, then this small object will not be disappeared. It's still left. And this small, there are these two objects are disconnected in the original image, but after closing, this narrow, narrow valleys could be mapped. And then you see there are hole. There is a hole here, another hole here. And then this hole is a little bit smaller and this is a little bigger. And the smaller holes could be mapped by dilation. And then the completely mapped hole, completely filled hole cannot be recovered because the hole was disappeared. Then after dilation, even though the erosion was applied, then the hole is not going to be appeared. So we say this is closing because the holes will be closed. And we say this is opening, and because this makes the holes bigger, or small gaze bigger. Okay, thank you for listening. And we just finished the second week's class, the fundamentals. So from the next week, we are going to study about convolutions and spatial filters. Okay, thank you very much and see you next time. Bye.